chemical flame retardants can leave behind their own impact on the environment.
But researchers have come up with a greener way to fight fires.
Dr. Brian Lattimer, the director of the Extreme Environments and Materials Lab at Virginia Tech, is one of those engineers. We're really interested in this. Thank you so much for being here. You know, there's been a lot of talk about PFAs, or forever chemicals, in things like drinking water. But apparently there are also components of the fire suppression systems that we see firefighters use. So what kind of impact do they leave behind after the flames are contained?
Well, thanks for having me on today. I think one of the big things with PFAS and firefighting foams is they're very mobile because they're in these aqueous solutions. And so they're able to go down into the ground, filter through the soil, can get evaporated up into the sky. And so that's they're very effective at putting out fires, but I think what we're finding is since they're biopersistent, bioaccumulative, they're just not feasible to keep using.
Now, as you were researching a way to kind of slow down fires without those chemicals, what did you learn about how they spread that helped you focus in a greener suppression system?
Yeah, that's a great question. One of the things that we hypothesized is that we need to design new molecules that prevent the fuel vapors from coming up through these foam blankets. And so the way these firefighting foams work is they basically smother the fire by covering it with this foam. And so we're designing these new molecules with machine learning and analytical techniques so that they can prevent the fuel from going up through this foam blanket, and the fuel can sometimes also degrade the foam. And so we're designing these molecules so that they have really good characteristics for that.
So how does this material coming from the Virginia Tech Extreme Lab, how does it specifically work? And what actually makes it better for the environment?
Yeah, so what we're doing is designing something called a molecular toolbox, and I'm working with my colleague Rui Chow here at Virginia Tech and Tim Long at ASU to put together this set of tools that chemists can actually use to accelerate the design of new molecules. And so along the way, we're discovering new molecules that have these certain behaviors. But this is really just the beginning of giving chemists all over the world the ability to design these molecules more rapidly and come up with better and better solutions.
Now, we're certainly seeing fires in all sorts of different communities, from the flatlands or the plains. You got mountain towns. How does this material adapt to different environments, if it does at all?
So it's really these kind of firefighting foams. There's a lot of different kinds of firefighting foams, but these ones that contain PFAS have historically been used at airports all over the world, transportation applications where you might have a tanker truck involved. And so fortunately, they're designed so they're capable of being used anywhere. And so when we come up with these new molecules, we also need to make sure that they're able to operate in all those different conditions as well.
Yeah, we have it seems like, growing wildfire threat every year. So is it feasible and scalable to create enough material to keep up with that growing threat?
Yeah, I think that, having new strategies and new chemicals that you can put on before these fires start to get near communities, having that capability is really one of the big focuses. So when you look at firefighters trying to manage wildland fires, really usually doing it around communities and protecting communities. So that makes the design space a little bit more feasible. So I think it's definitely possible, but it's a tough problem.
Yeah. Well, many thanks to you, Dr. Brian Lattimer, the director of the Extreme Environments and Materials Lab at Virginia Tech. Very interesting. And I also think